Welcome back to Very Ordinary Differential Equations. In this lecture, we learn how we can use Laplace transforms to solve non-homogeneous first-order linear systems with constant coefficients. There's no real surprises, to be honest. If you have the system y prime equals ay plus f, taking the Laplace transform is no different than it has been before. Here, f is our column of forcing functions. Our notation, as we've used before, the Laplace transform of little y is capital Y, and the Laplace transform of that column of forcing functions, little f, is going to be capital F of s. So take the Laplace transform of both sides. On the left, do what we've done before. On the right, we rely on linearity and factoring out the constant matrix A. Our goal is to solve for capital Y of s, so we move every term with capital Y of s to one side and every term without it to the other. Assuming S is not an eigenvalue of the matrix A, then we can invert Si minus A and multiply by that inverse matrix, the resolvent matrix. So here's where we are so far. The Laplace transform of our solution is given by the resolvent matrix times the initial state plus the forcing functions. We do have to be a little careful using linearity of all of our operators because matrix multiplication is not commutative, so left versus right really matters. Just be careful about that. The distributive property, however, holds perfectly well, so we distribute the matrix Si minus A inverse. Now I can take a Laplace transform of both sides. On the left, taking the Laplace transform of capital Y brings me right back to my solution. This was the goal, to find y of t. This looks very familiar. This is what we discussed in the previous video. On the right, however, we have this new term, the inverse Laplace transform of the resolvent matrix times the Laplace transform of the forcing functions. So here's where we are so far. Since y of 0 is a constant column, you can factor it out on the right and end up right here. This is starting to look pretty familiar. Now that first term is the state transition matrix multiplied by the initial values. It's the solution to the homogeneous equation y prime equals ay. That other term, the inverse Laplace transform of the resolvent matrix times capital F of s, now accounts for the forcing function little f of t. Therefore, what we have is something that looks like what we've done before, where the general solution to a differential equation was given by the general solution to the homogeneous differential equation plus one particular solution to the non-homogeneous equation. And that's kind of what we have here. A general solution to the homogeneous linear system plus something that accounts for the forcing function, little f of t. For our first example, let's solve an initial value problem. Y prime is a given matrix times y plus a forcing function of e to the 2t and e to the 5t. Also, we have initial conditions. Y of 0 is the column 1 and negative 1. Well, our general solution is of this form right here, so we need to attack this piece by piece. We're going to need the resolvent matrix, Si minus A inverse. We need it twice. Here, to take the inverse Laplace transform, and here, to multiply by capital F of s and then take the inverse Laplace transform. Well, Si minus A is given by the following matrix. Since it's 2 by 2, we can use our familiar formula to invert it. So here is the resolvent matrix Si minus A inverse. The denominator factors as s minus 1 times s minus 4. That's good to know. Now, for the state transition matrix, we're going to need to distribute that denominator in and apply partial fraction decomposition to every term. If you go ahead and do all of that, there is a common factor of 1/3 that comes out. But partial fraction decomposition, having distributed this denominator into every term, results in the following matrix. Okay, it's fairly tedious to do, but it is doable. So here is the resolvent matrix after applying partial fraction decomposition. Then we can compute its inverse Laplace transform pretty quickly. So here is our state transition matrix, 1/3 times all of these various exponentials. And we knew these exponentials were coming having done this partial fraction decomposition and denominators of the form s minus 1 corresponding to e to the t and denominators of the form s minus 4 corresponding to e to the 4t. We can now state that the state transition matrix, inverse Laplace transform of the resolvent, times our initial condition of 1 and minus 1 actually simplifies rather beautifully. If you take this matrix and multiply by 1 minus 1, you'll just get e to the t minus e to the t. So here is our general solution to the homogeneous linear system. But take a step back. Before we distributed that denominator in and applied partial fraction decomposition, here was the resolvent matrix. Because the non-homogeneous term involves multiplying by this capital F of S before taking the inverse Laplace transform. So all of that partial fraction decomposition work that we did isn't actually useful for this term. So first, let's compute capital F of S. It's just the Laplace transform of the forcing function. Easy enough. 1 over s minus 2, 1 over s minus 5. Then what we need to do is take the resolvent matrix, compute it up here, and multiply it by this column f of s. If you take this matrix and multiply by the column, well, over here, we still have that same 1 over s minus 1 times s minus 4. If you take this matrix and multiply by 1 over s minus 2, 1 over s minus 5, you'll end up with this column right here. So here is the resolvent matrix times the forcing function Laplace transform. Now we distribute and apply partial fraction decomposition. Okay, notice we do just have a column now, not a 2 by 2 matrix. Having distributed that denominator and applying partial fraction decomposition to both rows, this will be the result. Now we can take an inverse Laplace transform fairly directly. So this was the matrix we got by the resolvent matrix times the Laplace transform of the forcing function, having applied partial fraction decomposition to every term. So now we take an inverse Laplace transform and it's pretty quick. Okay, so we just end up with that 1/6 factoring out. Otherwise, negative e to the t minus 2 e to the 4t plus 3 e to the 5t and so forth for the second row. Now we can combine all of the work that we've done. This is the general form for solutions, and we have computed each term. This was the general solution to the homogeneous linear system. This is the term corresponding to the forcing function. We've computed both of them. Okay, the solution to the homogeneous system was pretty simple. The solution for the forcing function, a little less simple. And if desired, you can now combine these into a single column vector. So here is our solution, y of t. For our second example, solve the following initial value problem where we have a lot of ugly things going on. We've got a 3 by 3 matrix, which means that computing the resolvent is going to need Cramer's rule. Also, we have forcing functions of a bunch of different types. So we do need to compute that resolvent, Si minus A inverse. Now here's Si minus A. Inverting this matrix is pretty awful. We're going to use Cramer's rule, however, and term by term by term, hack your way through it. I'm skipping all of that work. Here is Si minus A inverse. So there we have it, Si minus A inverse. We do, remember, need to divide every term by the determinant of Si minus A. So this denominator here is the determinant of Si minus A. And then otherwise, we've got alternating signs applied to determinants of those matrix delta ij. So here was our resolvent matrix. There is some simplification to be done inside the matrix. Once you do that simplification inside the matrix, we need to compute two different things. We need to compute the general solution to the homogeneous linear system. Then we need to compute the Laplace transform of the forcing function column, multiply it by this resolvent, and take the inverse Laplace transform of that. So for the first one, we're going to distribute this denominator in and apply partial fraction decomposition to every single term. Then I can just take the inverse Laplace transform directly. So here was our resolvent matrix. If you distribute that denominator in and apply partial fraction decomposition to every single term, here is the giant monstrosity that will result. And hopefully it comes as no surprise that I am not doing this by hand. I used a computer to generate all of these. Now I can compute the state transition matrix by taking the inverse Laplace transform of this enormous mess. This step actually isn't that hard. Terms with denominator s minus 5 will generate e to the 5t. Denominator of s minus 5 squared corresponds to t e to the 5t. And so we just hack through and see what we get. And here's what you get. Okay, there's a common factor of 1/5 that makes this a little easier to write. So factor that out of everything. And there's your inverse Laplace transform, in other words, your state transition matrix. Now what we need to do is multiply that state transition matrix by the initial state y of 0. So here was the state transition matrix, 1/5, this enormous thing, but our initial conditions were actually pretty nice, 1, 0, 0. So multiplying this is going to be very straightforward. It's simply going to extract the first column. And then I redistribute the 1/5 back into the first column because it can be done with no real difficulty. So here is the solution to the complementary homogeneous linear system. So we computed the resolvent matrix, here it was, before we did all of the partial fraction decomposition, because in the non-homogeneous term, we're going to need to multiply by the Laplace transform of this column before taking the inverse Laplace transform. So we need to compute capital F of S. It's the Laplace transform of our forcing column. We just go term by term, 1 over s minus 3, 1 over s plus 2 squared, and 1 over s squared plus 1. Now we can take the resolvent matrix and multiply by the column we just computed. So here is the resolvent matrix. Here's the column we just computed. If we go ahead and do this matrix multiplication and then distribute the denominator inside, we'll end up with all of this. Okay, so here is the resolvent matrix times this column. It's a pretty ugly matrix, and as I specified, I'm using a computer system to do a lot of the grunt work for me here. Now, the matrix we generated on the previous slide, every row was the sum of various terms. We need to give them all a common denominator. Oof, there it is. Now what we're going to do is expand and simplify all of the numerators, which transforms the matrix into this terrible, terrible thing. Well, what do we need to do next? Partial fraction decomposition of every term. And you can bet, again, I am not doing this by hand. Well, if we apply partial fraction decomposition to every term, here is the just incredibly ugly mess that we are presented with. However, at this point, taking the inverse Laplace transform is thankfully pretty straightforward. So if we take the inverse Laplace transform, we just go term by term, generating things like e to the 5t, t e to the 5t, e to the negative 2t, and so forth. Taking the inverse Laplace transform of the terribly ugly matrix on the previous slide makes the slightly less terribly ugly matrix here. And finally, we're in a position to state our solution. The solution is given by the solution to the complementary homogeneous linear system plus the solution with the forcing functions included. And there it is. Okay, so here was the solution to the complementary homogeneous system. It was pretty straightforward. And here was what we got from this second term that involves the forcing functions, and it was not very nice to look at. However, this example was made to try to be pretty ugly. The forcing functions involved e to the 3t, t times e to the minus 2t, and a sine function. Notice that e to the 5t was the only exponential that was a solution in the complementary homogeneous system, so at least I didn't use any forcing functions that were solutions to the homogeneous linear system, but otherwise this was built to just be a real mess, and it was. So that's enough of problems quite this terrible. For our third example, let's go back to a 2x2. Here is our system. However, notice that the forcing function involves step functions and an impulse. However, our initial conditions are all 0. But with a step function and an impulse, even as we learn other techniques to solve non-homogeneous systems, Laplace transforms are going to be the way to go for this one. So we need to compute the resolvent matrix. Since it's just a 2x2, this is going to be pretty straightforward. So here's Si minus A, which we invert using our traditional formula, and there it is. So there's no point in computing the state transition matrix in this problem, however, because our initial condition is all zeros. So our state transition matrix would be multiplied by this column, which will totally vanish. So the state transition matrix is totally irrelevant in this problem. With your initial condition being all zeros, that step is no longer necessary. So here's the resolvent matrix. We do need to compute the Laplace transform of the forcing function. All right, so going term by term, Laplace transform of e to the t, 1 over s minus 1. Here, notice what we have is a shift with an appropriately shifted function here. So what we end up with is an e to the minus 2s, that comes from the step function, times the Laplace transform of the unshifted version, which would just be e to the minus t. And the Laplace transform of e to the minus t is 1 over 1 plus s. Okay, and the Laplace transform of e to the minus 3t, and the Laplace transform of an impulse function correspondingly. So here is capital F of s, it's this column. Then we can compute the resolvent matrix times that column. We're leaving the 1 over s minus 1, s minus 2 outside for the time being. Just take this matrix here, s minus 2, 4, 0, s minus 1, multiply it by this column, and here's the result. All right, so here is the resolvent matrix times the Laplace transform of the forcing function column. Now we can distribute and apply partial fraction decomposition. Remember that when we had step functions and impulses, it was handy to keep exponential terms, where the exponent is out here, separate from the terms that are just purely rational functions. So when we do that, we distribute this denominator in and apply partial fraction decomposition. We'll end up with various rational terms, and then a couple of different exponential functions times other rational terms that we apply partial fraction decomposition to. Then we can take an inverse Laplace transform. Term by term, it's not so bad. T e to the t minus e to the t, and so forth. When you get to these exponential terms, remember that those correspond to step functions with shifted versions of inverse Laplace transforms. So now we have the inverse Laplace transform of the resolvent matrix times the Laplace transform of the forcing functions. And remember that since our initial state was all zeros, the state transition matrix times that would be 0, which is why we didn't bother computing it. So the entire solution to this problem is given by the term we already computed. There it is. Here is the solution to this initial value problem. All in all, we can take the Laplace transform of a non-homogeneous system just as well as we could take the Laplace transform of a homogeneous system. The relevant matrix inversion and partial fraction decomposition begins to become wildly impractical to do by hand, except for the simplest 2x2 examples. The procedure for every step, however, and therefore all steps put together, can be automated. All the solutions we went through today, all of the matrix inversion, partial fraction decomposition, I was simply using a computer algebra system. Okay, so if you are interested in using Laplace transforms to solve large systems of differential equations, you're going to automate the process.